Alright, now in this lecture we're going to continue looking at the Mann-Whitney test. But instead of looking at the exact test, which we've looked at in the last two lecture videos, we're going to look at a large sample approximation to that Mann-Whitney test. Now table A10 is used in performing the exact Mann-Whitney test, and the table is constructed in such a way that the total sample size is at most 30. And so we can use that table when we have a situation where the total sample size is no more than 30. But if we've got larger sample sizes, then we're not going to be able to use that particular set of tables. But that's not going to be a problem for us, because if we have more than 30 observations, then even though we don't have the table, we can use this large sample approximation. Now, this large sample approximation to the test is based on a normal distribution approximation to the true sampling distribution of a particular test statistic that we're going to look at. And in this context, because we're not tied down to the table, and therefore we don't have to define a test statistic that is completely in lockstep with that table, we are going to use a slightly different version of the test statistic than we did in the exact test. So I really want to point that out. This third bullet point here, because we're not tied to the table when we use this approximation, we're going to use a different definition of the test statistic t in this procedure. And basically the test statistic is just t1. So we can either denote it by t1 in these notes that are to follow, or we can call it t. But just keep in mind that for this large sample approximation, we are using a test statistic equal to t1 in all cases. One more thing I want to point out is that we can use this large sample approximation even if the total sample size is less than 30. Certainly as the sample size increases, the approximation is going to improve in general, but we're going to find that we don't have to restrict its usage just to those situations where the total sample size exceeds 30. On the other hand, if we have a situation where the total sample size is greater than 30, then we obviously cannot use the table. And so we have to use some other means, either a computer program or looking up another table, although we would have to make sure that we find a table that is consistent with the way that we're doing the analyses, which could be problematic because, again, this procedure that we looked at in the exact testing case is based on that particular table, which came out of the original paper upon which this was developed. So anyway, if we do have a total sample size that exceeds 30, then I think we're going to find that this large sample approximation is very, very adequate, and we're not going to have to bother to find a different table, and we may not even have to use software to get a really good result. And so one thing that we have to do in order to utilize this large sample procedure is something that should remind you of what we did when we looked at the normal approximation to the binomial distribution. And back in that situation, we approximated probabilities involving a binomial random variable by essentially superimposing over the graph of the PMF of the binomial distribution a normal distribution that has the same mean and same variance as that binomial distribution. And then after we did that, what we did was we approximated areas under that binomial PMF with corresponding areas under the normal PDF. Well, that's the same kind of thing that we're going to be doing here. Now, in order to do that, in order to superimpose over the true sampling distribution of our test statistic t, to superimpose over that the appropriate normal distribution, we have to know the mean and the variance of that sampling distribution of t so that the normal distribution that we superimpose over it has that same mean and variance. And so here are formulas for the actual mean, variance, and standard deviation of the sampling distribution of our test statistic t under the conditions of the null hypothesis. Now remember that the null hypothesis that we're looking at here says that the two populations are equal, they're the same. They're the same in every way, including their location. So when that null hypothesis is true, then this test statistic t, which again is t1, and remember what t1 is. T1 is the rank sum for what we're calling sample 1. And so the mean of the sampling distribution of t is given by this expression, n1 times n1 plus n2 plus 1 all over 2. The variance of the sampling distribution of t is n1 times n2 times the sum n1 plus n2 plus 1. All of that over 12, and then the standard deviation of the sampling distribution of t is just the square root of the variance. So we have identified the mean, the variance, and then the standard deviation of the sampling distribution of t computed under the assumption that the null hypothesis is true. Then what we're going to do, instead of using the test statistic t, we're going to use a standardized version of it. And again, even though the formulas are different, all of this should look very, very familiar to you because this is the same procedure that we used in developing the normal approximation to the binomial distribution. Okay, so instead of using t, we're going to use a standardized version of it. And so we take the random variable t and we subtract from it the mean of its sampling distribution and then divide that difference by its standard error. And so I plugged in the formulas from the previous slide. We're going to call that z-calc. We're going to have our rejection criteria. So for the two-tailed test, the null hypothesis being that the two populations are the same, the alternative hypothesis being that the populations differ in terms of their locations, then we're going to reject the null hypothesis if z-calc is either really small, in other words, if it's less than negative z sub alpha over 2, or if it's greater than positive z sub alpha over 2. Now, the p-value formula should look very familiar to you. It's just 2 times the probability that a standard normal random variable is greater than or equal to the absolute value of the observed value of z-calc. If we have a right-tailed test, and by the way, in this particular large sample approximate framework, because we're not tied to the table, and remember that the table is set up so that everything was a left-tailed test, but because we're not restricted to that kind of procedure in this large sample situation, this approximate test, the terms right-tailed test and left-tailed test have their familiar meaning, so we're going to utilize that terminology. So for this right-tailed test, again, the null hypothesis is the same in all 3 cases here. And this is so the null hypothesis is that 2 populations are the same, but in this alternative hypothesis, the alternative is that population 1 is shifted to the right of population 2. So we're looking at a very specific direction in which there is a location shift, shifted to the right. And so in that case, this is a right-tailed test. So we're going to reject for large values of our test statistic z-calc. And so for a significance level of alpha, we're going to reject if z-calc is greater than the upper alpha percentage point of the standard normal distribution, which is z sub alpha. The p-value for this right-tailed test is as you would expect, because this is based on the reference distribution being the normal distribution. So this p-value formula, the p-value is the probability that the standard normal random variable z is greater than or equal to the observed value of z-calc. And then finally for the left-tailed test, in this case the alternative says that population 1 is shifted to the left of population 2. So again, it's this very specific direction that we're thinking about here, in this case shifting to the left of population 2. This is a left-tailed test, and so we're going to reject the null hypothesis if our test statistic is small. In other words, if it's less than negative z sub alpha, the p-value formula is equal to the probability that the standard normal random variable z is less than or equal to z-calc. So that is the procedure. If you go back and look at your notes from your first methods course, and if you look at a hypothesis test about a population proportion, or for the z-test of a population mean, all of this should look very, very similar to that, because those tests are based on the standard normal distribution being the reference distribution. And so we are doing the same kind of approximation. We are approximating the sampling distribution of T1 using the appropriate normal distribution. And when I say the appropriate normal distribution, it's the normal distribution that has the same mean and the same variance as the true sampling distribution of T1. And then we standardize everything so that we get back to the standard normal. That's why this procedure looks virtually identical to those procedures that I just referred to from your first methods class. Now let's look at a few examples, and we're going to revisit examples 3.1 and 3.2. Right? We've already seen those. We've done those tests. We've done the Mann-Whitney test, the exact test, using table A10. Now we're going to revisit these examples and use the large sample approximation to that Mann-Whitney test. So we're still doing a Mann-Whitney test, but we're approximating. And so let's take a look at this. We're comparing the strengths of cables made from 2 different alloys, and the question of interest is there a difference in the distributions of the strength of the cables made by the 2 alloys? And in particular, we're looking for a difference in location. And what we're going to do is we're going to use the large sample approximation to the Mann-Whitney test in order to answer this question. The large sample approximation to the Mann-Whitney test uses the normal distribution that has the same mean and same standard deviation as T1 to approximate the true sampling distribution of T1 under the conditions of the null hypothesis. So that's what I've been saying several times here. And some questions may have come in your mind. We haven't yet looked at the true sampling distribution of T1, have we? What does it look like? What does the true sampling distribution of T1 look like under the null hypothesis? And how well should we expect the normal distribution to approximate the true sampling distribution of T1? In fact, if you think back to it, I said we can even apply this large sample approximation when the total sample size is less than 30. And that may have been a surprising statement to you. So how good is this approximation? What can we expect from it? What kind of performance can we expect from it in terms of accuracy? And what motivates this approach anyway? I mean, you might think, well, it's got to be something to do with the central limit theorem, and it does. But one thing we have not done in looking at this test is we really have not investigated, in much detail at least, what the sampling distribution of T1 looks like. And we're going to look at that in the next slide. We're not going to prove this. We're not going to go into a detailed development of this. But what I'm going to do next is I'm going to show you in this next slide, we're going to see for this particular situation. Remember what this situation is. We've got a total sample size of only 18. N1 is 8, N2 is 10. So the total sample size is 18. What does the true sampling distribution of T1 look like under the conditions of the null hypothesis? That is the context under which we're talking about this true sampling distribution of T1. So what does the true sampling distribution of T1 look like under the conditions of the null hypothesis? And here it is. This is the true sampling distribution of T1 for this situation under the conditions of the null hypothesis. Take a look at that graph. Now, if we superimpose a continuous normal distribution on top of that, they're going to look very similar, aren't they? And so that is the reason we can utilize this procedure. So the true sampling distribution of T1, while it's a discrete distribution, looks very similar to a normal distribution. And so we can therefore expect the normal distribution to provide a good approximation to the true sampling distribution of T1. Therefore, the large sample approximation to the Mann-Whitney test should provide results very close to those provided by the actual Mann-Whitney test, even though the sample sizes are only 8 for the first sample and 10 for the second sample, a total sample size of 18. Even for this small of a sample, I think you would agree that that looks pretty doggone normal. So this is the motivation. In order to do this analysis, we need the two sample sizes and then the test statistic, which is T1. We found that previously to be 106. Right? Remember that T1 is the rank sum for what we're calling sample 1, and we've ranked the data before. So you do have to rank the data, obviously. You've got to get those ranks. The rank sum for sample 1 was 106. The mean of the true sampling distribution of T is equal to 76. And the standard deviation of the true sampling distribution of T is 11.2546, rounded to 4 decimal places. This is a two-tailed test. We're going to perform this at the 0.05 level of significance. So the critical points are negative 1.96 and positive 1.96. The test statistic, to get this, to calculate zcalc, again, we plug in the value of T, which is T1, 106. We subtract off the mean of its sampling distribution. We subtract off 76. We divide that difference by the standard error, the true standard deviation of the sampling distribution of T, again, 11.2546. And so our test statistic value is 2.67. The p-value is equal to twice the probability that a standard normal random variable is greater than or equal to the absolute value of the observed value of our test statistic, right? So 2.67. And if we look that up in the standard normal table, we're going to get 0.00379. And so we get a p-value of 0.00758. So since 2.67, the test statistic, does exceed 1.96, Or equivalently, since the p-value, which is 0.00758, is less than or equal to the significance level we're using, 0.05, the rejection criteria have obviously been met, and therefore we reject the null hypothesis. And so we can say that there is sufficient evidence at the 0.05 level of significance to conclude that a difference exists in the cable strengths of the two alloys. So if we think of the distributions of cable strengths, there's a difference in location. Now we're not specifying which way, but we could certainly draw that conclusion based on the sign of the test statistic, because that's positive, and because we're expressing things in terms of t. A had the smaller sample size, so population 1 corresponds to population A, all right, and so alloy A gives stronger, in general, cable strengths. Now, one more thing I want to talk about. We've seen here that the p-value based on the large sample approximation, based on the normal distribution, we found that p-value to be 0.00758. Now, I just want to emphasize that this is an approximate p-value. It's approximate because we're using an approximate test. And what is it an approximation to? Well, it's an approximation to the true p-value, which if we had access to the true sampling distribution of t, then we could compute that. Now, we are not spending time in this class to derive the true sampling distribution of t in these situations. That's why we're using the table, so that we don't have to do those derivations or constructions, because again, it's a bit cumbersome and kind of difficult. It's certainly a little bit time consuming. But I do want to say, because look, I did show you that graph, right? I showed you the graph of the true distribution, the true sampling distribution of T1 under the conditions of the null hypothesis. That's it right there. So based on that, we could find the true p-value for this test, and the true p-value is 0.00622. So we see that the approximate p-value is not exactly equal to the true p-value, but it is fairly close, and because the approximate p-value is so much easier to calculate, it's really not even worth taking the time to compute this exact p-value unless we already have the software to do it. So what we're showing here is that this approximate procedure, this approximation to the Mann-Whitney test, does a very, very good job for us, and it doesn't take long to do it all. All right, so that's the end of example 1. Now we're going to look at example 2. This was the taste test comparison for 2 types of hamburger substitutes. Again, we're going to utilize the large sample approximation to the Mann-Whitney test. And so again, we've got the same data, the hamburger types. We've got 5 samples of hamburger type A, 5 samples of hamburger type B, and then we've got the ratings here, the scores, and they were ranked 1 through 10. So that is the data. The question we're going to answer is, use the large sample approximation to the Mann-Whitney test to determine whether there is sufficient evidence at the 0.05 level of significance to conclude that the 2 types of burger substitutes differ in terms of their quality of taste. Again, let me show you, for this particular situation, what the true sampling distribution of T looks like. Now remember, we do not have what we would typically consider to be a large sample. We've got a sample of size 10. We've got 5 observations from sample 1 and 5 observations from sample 2. But here is the PMF of T under the conditions of the null hypothesis. Obviously, T is a discrete random variable, and so its PMF is going to look discrete because it is discrete. But again, if we imagine superimposing the appropriate normal distribution on top of that, I think that we would agree that we would probably get a pretty good approximation of probabilities that we compute for this distribution. So we can expect this large sample approximation to do a pretty doggone good job even for this total sample size that's equal to 10. Okay, so again, we need the sample sizes. N1 is 5, N2 is 5. We need the value of the test statistic T. T, by definition, is T1 in this case, in this whole large sample procedure that we're looking at. And for this example, for this problem, that was 17. We calculate the mean and the standard deviation of the true sampling distribution of T. All right, so the mean is equal to 5 times the sum 5 plus 5 plus 1 over 2. All right, so 27.5. The standard deviation of the sampling distribution of T is equal to 4.7871. Again, this is a two-tailed test at the 0.05 level of significance. So our critical points are, again, negative 1.96 and positive 1.96. Now, this is one of the reasons why using standardized test statistics are so nice. Because even though, if you think about this example now and the previous example, completely different sample sizes. And if we were using the table, we had to look up different critical points. But when we're using this large sample approximation and using standardized test statistics, we end up using the same critical points. And so that makes the procedure a little bit easier to deal with. All right, so in this case, the test statistic is equal to negative 2.19. The p-value, using the p-value formula, twice the probability that the standard normal random variable z is greater than or equal to the absolute value of negative 2.19. If we look that up in the table, we'll get 0.01426. We multiply that by 2, and so the p-value for this test is 0.0285. Now, again, if you think about it, in the exact procedure that we looked at, where we use the table, we don't get access to a p-value. All we can do is calculate the test statistic, look up the critical point, and then make our decision based on that. But this large sample procedure gives us a way to get a much better approximation to that true p-value of the test. And so based on this large sample approximation, our approximate p-value for this test is 0.0285. And so since negative 2.19 is less than negative 1.96, or equivalently, since the p-value, which is 0.0285, is less than or equal to 0.05, the rejection criteria have been met. And so therefore, we reject the null hypothesis and conclude that the alternative is true. And so we can say that there is sufficient evidence at the 0.05 level of significance to conclude that a difference does exist. Now this says cable strengths. Okay, this is a copy and paste there. There's a difference in the quality of the taste between the two hamburger types. And so I'll just say the magic word abracadabra. And so then that is fixed now. There is sufficient evidence at the 0.05 level of significance to conclude that the two hamburger substitutes differ with respect to their quality of taste. Now again, let's compare the approximate p-value that we've obtained using this large sample procedure, which was 0.0285. Compare that to the true p-value for this test based on the true sampling distribution of t. And again, we're not going to go into the construction or derivation of that, but again, this is a picture of that true sampling distribution. And so based on that, the true p-value for this test is equal to 0.03174. So we see there is a difference, but it's not terribly large. And it's not too bad considering that the total sample size is only 10. So I think that's really encouraging when we think about when we might be able to use this approximation to the Mann-Whitney test. Anyway, that wraps up example 3.2. What I want to do to continue thinking for just another minute or two about when can we use this large sample approximation to the Mann-Whitney test. We say it's a large sample approximation. And really what we're saying here is that as the total sample size gets larger and larger, then the approximation should get better and better. Now the question is, how large do the two sample sizes have to be in order for this approximation to give us good results? Well, we've seen that even for a total sample size of 10, where we've got an even split, 5 and 5, it does pretty well. Now, if you've got an uneven split, you've got to be kind of careful, because if you've got a small overall sample size, then an uneven split can cause problems. For example, if we had 2 observations in one and 8 in the other, then it probably would not be a good situation to apply this approximation. But the larger both sample sizes are, the better the approximation is going to be. And let me also say that when we do these kinds of tests, these kinds of comparisons between two populations, where you've got independent samples, one sample from each of your two populations, in general, from a design standpoint, in thinking about power and things like that, power and precision, you're going to have the greatest power and the greatest precision if you've got an even split in your total sample size. So if the two sample sizes are equal. Now, that's not always possible for a variety of reasons, but I just wanted to tell you that that is, in general, the case. If you've got equal sample sizes, that is really the best situation from the standpoint of power and precision. So we've seen an application of this approximate procedure, this large sample approximate procedure, to a situation where we had a total sample size of 10 with an even split, and then a total sample size of 18 with not quite, almost but not quite an even split. We had 8 in one and 10 in the other. But let's look at a few examples where we've got even splits, equal sample sizes for sample sizes from 20 up to 28. And so we'll look at the total sample size of 20, 22, 24, 26, and 28. And what we're going to be looking at here is we're going to be focusing on the graph of the PMF, the graph of the sampling distribution of T under the conditions of the null hypothesis. And we want to see the impact, the effect of this increasing sample size. And I want to ask you to think about what is happening to the quality of the normal approximation to that sampling distribution as this sample size gets larger and larger. And at what sample size would you be comfortable using this large sample approximation? And so here is the true sampling distribution of T when we have a total sample size of 20 observations, 10 in one sample, 10 in the other. So we have an even split. Well, that looks even better than when we had 8 and 10. And it should, because we have a larger overall sample size. Now I'm going to increase it, the overall sample size, from 20 to 22. You see that? Look, it's getting better. Now we're going to increase it from 22 to 24, from 24 to 26, and from 26 to 28. So the table A10, goes up to a total sample size of 30, but I think that you would agree that we could probably use this large sample approximation for total sample sizes less than 30 and still get an awfully accurate result. And certainly if we have a situation where the total sample size exceeds 30, so we're not able to use the table at all, then we should feel very, very comfortable using this large sample normal approximation to the Mann-Whitney test. You might say, well, what about 30? Why didn't you do 30? That's the maximum in the table. Well, I tried. But let me look here. I got to do a quick calculation on my calculator. Yeah, well, okay, so in order to do that, my computer was going to have to construct over 155 million different possible samples. And I tried that. I started it and came back a little later, and I had a message up on my computer screen that said that it was out of resources. So anyway, we're not going to fool with that anymore, but you can tell it's going to get even better than this. All right? And so we should feel very comfortable using this large sample approximation to the Mann-Whitney test. Okay, so the Mann-Whitney test, remember, is a non-parametric test that we can use to compare two populations with respect to location. We use it in those situations where the samples are independent. They've been selected independently from one another. And this procedure does not make any assumptions about really any of the characteristics of the underlying populations. We're not making assumptions about the shape, certainly, or the heaviness of the tails, because we're basing the analysis on the ranks of the data in the combined sample. And so we don't have to worry about non-normality at all. When I say that, we don't have to worry about non-normality of the underlying populations. But anyway, I think you see the utility of this. We see that we do not need to depend on the normality assumption about the underlying distribution in order to perform this test. It completely frees us up from having to do that. Okay, so this is how we compare two populations with respect to location. In the next set of videos, we are going to generalize this to the situation where we've got more than two populations. And so if you think back to your first methods class, when we went from the two-sample t-test and generalized that, what was the topic? The topic was analysis of variance. It was comparing the means of two or more populations using analysis of variance. And so in the next set of lecture videos, we're going to be looking at the non-parametric alternative to that analysis variance solution. All right, so I'll see you in the next lecture video.